Hey everybody, welcome back to another round of Robison Rants. And yeah, as promised, I've got a couple of example problems for you just to develop more intuition about working with this AC circuit stuff. So go ahead. You have in front of you a what almost looks like a Wheatstone bridge, except now we have resistors, inductors, and capacitors. So take a minute, pause the video, see if you can come up with expressions for the currents and the potential drops in this circuit. You got it? Good, 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 good. So part of the reason why I chose this circuit was to give you an example problem that deals with a pi to t transformation, or if you prefer, a delta to y transformation. So yeah, let's go ahead and do that. And I'll choose this bottom delta to concern myself with. So just to give you an idea, this time I'll go ahead, I'm going to do a delta to y transformation. Then I'm going to go ahead and combine the impedances to get a single impedance, and that will give me the I naught value. And then I'll have to start working backwards to extract the rest of the currents. So I'm going to go through, like, if you will, the long way. Okay? And then maybe for kicks, we'll do it a second way, like node voltage, and I'll show you how to do this with a computer. So, okay, so let's go ahead. So first off, I said, hey, we have a delta to y conversion, and I said I was going to do it on this bottom triangle. So let me go ahead and first of all redraw this so that we're clear on exactly which side is dealing with what. So there's my capacitor, and I'll go ahead and label this node A. I'll call that one C, and I'll call this one D. In fact, instead of A, I'll call this one B as in boy. There we go. Okay, and we have a 20, we have a 60J here, we have a negative 20J. Okay. And if you recall from your lab, we have equations that give us the delta transformation into a y. Okay. And so this y will be like this. It'll be something like B with an impedance. And I believe impedances are usually just boxes. So I'll call that one Z1. I'll call this box Z2. And that goes to node C. And then I have down, and you can see that Y shape. This is Z3, and I'll connect that to node D. And so the question is, what values should I have for C, Z1, Z2, and Z3? Now, I didn't go through and derive this. The book takes care of that. But if we want, we can remember that Z1, so it attached to node B, what ends up happening is it's the multiplication of the adjacent impedances divided by the sum. So I go to node B and I look at the adjacent impedances, and I have to take a multiplication of those two. So I have 10 times 20 plus 60J divided by the sum of all of the impedances. So I have 10 plus 20, so that'll give me 30. And then I have a plus 40J here. And technically, that's it. Yeah, you have a little bit of simplification. You've got a 10, a 30, and a 40. So why don't we go ahead and just get rid of that? So the 10, so I could take out that 10 and I get 4J here. That's pretty spiffy, pretty nice. So go ahead, take a minute, write down what Z2 would be. Yeah, you got it? So again, the multiplication of the two adjacent impedances, the 10 times the 20 times the negative 20J. And again, this would be 30 divided by 40. The 30 plus 40J. And I'll go ahead and cancel out that 10. And so this is 3 over 4 again. Well, lastly, I'll go ahead. I'm going to write this instead of 20, I'll write this as 2 times 10. So then I can have that cancellation in there. So that's a negative 20j times 20 plus 60j. And the denominator doesn't change, the 30 plus 40j. And again, I notice I have that 10, so I'll go ahead and take those out. And so I get something like negative, I get something like negative 2j 20 plus 60j over 3 plus 4j. Okay. Sweet. So now we have successfully changed this bottom delta into a y. It's probably a good idea to redraw the circuit. So I'll go ahead and do that. Give me a second. Alrighty then. So the next thing that will probably be of use is we notice that we have these branches where several items are in series, namely the Z1 with the 4J capacitor and the Z2 with the resistor inductor combination. And so it would probably be useful for us to take these Z's and get the J's into the numerator. Now, the fortunate part is when we take the complex conjugate of the denominator, we have 3 plus 4j times 3 minus 4j. And so that will give me an answer of 25. Okay. So that'll be nice, 9 plus 16. Okay. And the reason that I say 25 is nice is because we see that we have a bunch of stuff that's divisible by 5. Okay. Alrighty then. So yeah, let's go ahead and simplify these suckers. So we have 5. I'm going to pull a common term of 5 out here. We have something like 5 times 4 plus 12j times 3 minus 4j, all divided by 25. So what do we get at the end of the day here? 1/5 12 minus 16j plus 36j. Let's see, 48 minus j squared. So that'll give me a plus 48. Okay. And so at the end of the day for Z1, it looks like I get something like 12 plus 48 divided by 5. So that gives me 12 plus 4j. So there's our value for the first impedance, Z1. Go ahead. Second one. Yeah, you probably already have it. We have a negative, I'll say 5 times 4j times 3 minus 4j, all divided by 25. And so we end up with something that says, okay, well, the 5 cancels. And so I get 1/5. We get 12j. 4 times 3 is 12. So I get the 12j. So I get 16 minus, negative 16, because I have that negative sign out front. So negative 16 minus 12j. And we'll just write that as 3.2, negative 3.2 minus 2.4j. And the last one, of course, 120. Let's see, 120 is 24. So we have 5 times 24 minus 8j times the quantity 3 minus 4j all over 25. And so we get something like 1/5. We got to put our hats on here. 72 72 minus, okay, so this is 96. Okay. So what I'm thinking of is 4 times 25, which is 100, and then I subtract 1 4 from that. So that's 96J. Okay. 8 times 3, so we get a 24J. And then negative 8 times negative 4 gives me a 32. And then J squared picks up an extra negative sign. So I get 32. And that whole rigmarole, 1/5. Sorry, I got to write this out, otherwise I'll make a mistake. Minus 120J. So we get something like 8 minus 24J. So there we go. So we now have all 3 of our impedances written with the, all 3 of our impedances written with the J's outside the denominator. Okay. Good. Well, now we're going to want to add resistors in series. So let's go ahead and do that. Okay. So for this left branch, okay, I'll say left for a moment. This left branch, what we have is a negative 4J capacitor, and added to that, we have our Z1, 12 plus 4J, which is rather convenient, don't you think? And our right branch, we have 63.2 plus a 2.4J. So that's the resistor and then the inductor. And then added to that, we have Z2, which was something along the lines of negative 3.2 minus 2.4J. And so we see the imaginary stuff cancels out and we end up with 60. So now what do we have? We have our power supply. And notice that was a 120 at 0 degree phasor. We have 2 branches, one which has 60 omega, and one branch that's at 12 omega, 12 ohms, excuse me. And then we go into Z3. Well, now notice there's no imaginary components to the left and right branches. We'd say that they're purely resistive. They don't have any imaginary components. And so now we have to just, add those in inverse. So 1 over 12 plus 1 over 60, negative 1. Well, let's see. That gives me 6 over 60. Right, 12 times 5 is 60, so I get 5 plus 1. And so I see that when I combine those two together, I get an overall resistance of 10 ohms. So last but not least, if I want to know the equivalent impedance of the entire circuit, I take my 10 ohms from that parallel branch at the top and add to it the value of Z3. So what do I have at the end of the day? I have 10 plus, and Z3 was 8 minus 24J. Or in other words, I get 18 minus 24J. There is my equivalent impedance for the entire circuit. Pretty cool, huh? let's go ahead and turn that into a phasor just so that we have an idea. So we could write this in polar coordinates as being, and you're probably fast on the ball here, faster than I am, 18 squared. What is the square root? 18 squared plus 24 squared. That's 30. So we have our impedance has a magnitude of 30. And let's go ahead and find out what the angle is. Arctan of 4/3. So I get a 53.1. And notice it's a negative, so the negative sign, so I get a negative 53.1. Whew. Well, hey, we now can find the potential or the current flowing through Z3. So it's a start. Let's go ahead. So let's find out. The current going through Z3 would simply be now the potential divided by the equivalent impedance. And so we get something that says 120 at 0 degrees divided by 30 at negative 53.1 degrees. Now you could do it in terms of the Cartesian coordinates, and then you just have to move the j into the numerator again. Okay. So that's perfectly valid. And so we see that the current flowing through our Z3 is given by 4 at an angle of phasor of 53.1 degrees. Sweet. Okay, good so far? Okay. So now that we have the current flowing through Z3, we need to solve for the rest of the circuit. Right, we're not done yet. So the next thing is, let's go ahead and get the potential drop. And I'm sorry, I should have labeled this as a lowercase I. Let's get the potential drop across Z3. That would just be Z3 times the current going through that impedance. Okay. So what do I have for Z3 again? Yes, I have 8 minus 24j. And then I have times this phasor. So right now, this is not probably the right way to do it. I've kind of mixed notations, right? This is Cartesian coordinates. This one's in polar coordinates. Let me go ahead and get this in polar coordinates. So we have the square root of 64 plus 24 squared. Okay, so it's a shade above 25. What we have is 25.3. And the angle that will be at is the inverse tangent of negative 3. So I get negative 71. 6. Now we're actually in the proper form, so we can do our nice little phasor relationships. We can multiply the magnitudes, so you get something like 101.2, and you add the angles. So whatever negative 71.6 plus the 53.1, so we get negative 18.5. Guess we could have done that one in our head. So there's the potential drop across the third impedance. Which means we now know what the potential drop is across what I referred to as the left branch and the right branch. Right? Because the potential drop, I will label that as V left that potential drop is going to be the potential of the source minus the potential drop across Z3. Okay, so what do we have there? We have the 120 at 0 minus this 101.2 angled at negative 18.5. Oh, shoot. Now we have a subtraction, so we're going to probably want to go to the Cartesian coordinates instead. So this is 120 plus, I'll put 0j, minus, and we have 101.2 cosine of 18.5. Notice I dropped the negative sign because cosine is even. And I have minus 101.2 sine of the 18.5, and that would be j. Okay. I didn't say it was a short problem. So yeah, you can see you get 120 minus 101.2. Well, let's just, you can see that. Let's just group our real and imaginary terms together. Okay. So we have 18.5. So what we want is 120 minus 101.2 cosine. And don't forget, make sure your calculator is in degrees. Many a student have been led awry due to that. So I have something that says 24 point, I'll round it to one decimal place. And then notice I have a minus minus, so that becomes a plus. And 101.2 sine of 18.5. So I get something that says this is 32.1j. Which means, okay, don't forget, that's for the left one, but that must also be for the right branch because they're in parallel. So now we go back a step and recall that the left branch had a resistance of 60, excuse me, the left branch had a resistance of 12, the right branch had a resistance of 60. And now that we have the potential drop, we could say the current in the left branch is simply equal to this divided by 12. 1/12 V left. And the current in the right branch, oops, excuse me, that got in the way. The current in the right branch is simply 1/60 times that potential difference. And here, it's nice because those are purely resistive. Right? So I don't have to worry about moving j's to the numerator or anything like that. So now what we have is we have successfully found the I naught, the current coming from the source. And notice that I left is also the current flowing through the, shoot, for lack of a better term, since the problem had them labeled, I'll say it's the current flowing, excuse me, I1. This would be I1. And the current right would be I2. Okay. So we're halfway done with the problem. So let me redraw the circuit just so that we know where we are now. We have our supply. We know this current, that would be I naught. We have the left and right branches, this one being 60 ohmega, this one being 12, and then we have our Z3 impedance. And we know now the values of the currents going through, that would be I1, and this would be I2. For completeness, I'll draw this over in blue again. There we go. So the next step, what do we do now? We're going to have to unpack even further. right? That's the only way to do these things, is that we have to unpack. So we look at the left side, for example. Okay. We know that this 12 ohm resistor is actually the combination of Z1 and the 4J capacitor. Right, we had the 4J capacitor in parallel with Z1. And the right branch is a 63.2 resistor, a 2.4J inductor, and then Z2. Okay, so now that we know the current flowing through each the left and the right branch, now we can find what the potential drop is across Z1 and Z2. Right? Yeah, you got it. It would be something like what I called V left minus, let's say I'm doing the left-handed branch here. Okay. So V left minus the current, I1, times the impedance of the capacitor, so negative 4J. That would equal the potential drop across Z1. Right? Potential drop across that branch minus the potential drop across the capacitor, that must equal the potential drop of Z1. And similarly, we could say V left minus current 2 flowing through the 63.2 resistor plus the 2.4J inductor, that must equal the potential drop across Z2. I don't know. Do you want to run through the numbers? You do? Okay, we can do that. Yep. So let's go ahead. So the potential drop across Z1 is equal to, we'll say V left, the potential drop across the entire branch. We have a minus minus, so I'll put a plus 4J. And then remember that I1 was simply V left, the potential across the entire branch, divided by 12. Right? So the potential drop across Z1 is simply the potential drop across the left-handed branch. And we'll put, I guess we'll put it like this. We'll put it as 1 plus 4J, and I'll write that whole thing over a common denominator of 12. And now you can see that 12 was the resistance of that entire branch. So you can imagine Z2 will just be the potential drop across the branch, what I called V left. And here it will be 60. Now I have a minus, so I got to be careful there. Minus 63.2 minus 22.4J. That entire rigmarole is going to be over 60. Cool, huh? Of course, I guess you could simplify that a little bit. This would be V left negative 3.2 minus 2.4J over 60. Sweet. Which means, okay, now we have the potential drop from what I called node, I believe, little. We now have the potential drop between node B, as in boy, and node C. Right? We know what the potential of node B is. We know what the potential of node C is. So we should be able now to get the current flowing between those two. So I've taken the liberty of rewriting these equations for you just so we have an idea about remembering these. And again, as I said, we have now the potential at C, B, and D in the sense of we know the potential drop across Z1. We know the potential drop across Z3, 3, and Z2. Okay. And by knowing the drop across Z1 and Z3, we now have the drop across the delta connection as well. Right? So we see that the drop between B and D is the Z1 plus Z3 drop. C and D is the Z2 and Z3 drop. And of course, B and C is the difference, Z1 and Z2. Okay. And here we have the difference because you could think of this as going from high to low, high to low, high to low. So going this route, for example, we would add them, but going across the center route, we would subtract. Okay, okay. So yeah, I'll go ahead and write out these drops. So we have an expression for V left, which I've written up here. And so if we actually do that calculation, we should get something like 13.3 plus 40.1J. And similarly for number 2, I got something. Excuse me, I just realized that I forgot to do a division in here. Oops. There we go. I got something like 0.004, so essentially 0 to 2 decimal places, plus 2.7J. And then, of course, we have VC3. We have that one right here. Now, of course, I left it like this instead of going into the polar form because we're going to have to do some adding. Right? So if we want the potential drop from B to D, okay, that is the potential drop across Z1 plus the potential drop across Z3. And now that I have my Cartesian expression for that, we can see that it's something like, let's see, 109.3. And then we have something like plus 8J. And similarly from C to D, which is VZ2 plus VZ3, we get something like, well, 0. So I get 96.0. And then you can see we get something like minus 29.4J. And lastly, as I said, you have BC, okay, across that horizontal branch. And we'll need the difference. So I'll do VZ1 minus the potential drop across Z2. And so you see, you get something like 13.3 plus 37.1J. And so now we can get rid of the y. Essentially, now that we have these drops between BD, CD, and BC, we can now get rid of that model of the y and go back to our delta model. Right? You can start modeling it like this again. Okay, well, I think that's gone far enough. We can see that now that we have the potentials at each of those nodes, we should be able to reconstruct the currents going through everything. Okay? I'll leave that last step up to you since we've gotten a couple of them and you can kind of get a feel for it. Okay? Good. So let's go back to way back when, and let's see if we can do this another way. Okay? And in particular, let's go ahead and start thinking about the node voltage method. So I'll go node voltage here. Now I choose this not for any particular reason, but just because I prefer that method over the others, just a personal preference. But let's go ahead and ground the bottom node and write out some equations. Okay? So for node A, we see immediately that the potential at A is going to be equal to the potential jump across the source. So I can just immediately go like this, right? Or if you prefer in Cartesian coordinates, just 120 plus 0j. And B, as in boy, again, let's play our old song and dance. You have VB minus VA over this negative 4j. Then we have plus VB minus VC over this 10 plus VB divided by our 60j. And that whole rigmarole equals 0. Well, similarly, C, let's go ahead and write this out. We have VC minus VA over, and we go 63.2 plus 2.4J. Okay. Plus VC over minus VB over the 10 plus VC over the negative 20j equals 0. Okay. Now, of course, we could do our sub and solve, our same old, rigmarole. Notice, and this is the reason why I thought, okay, well, I should do this as well, is notice that these equations, again, are linear, right? They're linear in VA, VB, and VC. And so our techniques for solving these equations haven't changed. Okay? Because it's linear, we can still apply our matrix techniques. So why don't we go ahead and do that? Okay. Now, here's the caveat. I don't know about your calculator. I know that my TI-82s and the TI-83 that I have on the computer won't do this. Okay. So some calculators, I suspect maybe higher like 87s or 89s might be able to do imaginary numbers in the matrices. This TI-82 won't do it. It gives me an error. Okay. So you'll have to check your calculator. Some calculators I do believe will do it. That being said, we could always throw this sucker up into MATLAB. Okay. MATLAB will certainly handle these kind of situations. So let's go ahead, take a moment, get this into standard form. Okay. You got it? Yeah, good. So standard form, I'll go ahead and I will put it as VA in the first column, VB in the second column, VC in the third column, and then, of course, my remainder, if you will, what I called lowercase b. So the first one is just 1, 0, 0, and 120. Our second one, we'd have something like 1 over 4j, and I'll just even leave this as a fraction. MATLAB is smart enough to figure it out for us. In the second part, I have negative 1 over 4j, okay, plus the 1/10 plus the 1 over 60j. And the third one, I have negative 1/10, and the whole rigmarole equals 0. Lastly, okay, and again, here's, okay, we got a little bit more rigmarole, 63.2 plus 2.4j. For b, we see we just have a negative 10th. And for c, we have something, the 63.2 plus 2.4j. Okay. And, okay, plus 1/10. And shamefully, I've run out of space again. And then we have the minus 1/20th j. And that whole rigmarole equals 0. Okay. So fortunately for us, there is our matrix. Let's go ahead and take a minute, put it into MATLAB. Okay. So it's always good to check. Okay. First of all, make sure you know what MATLAB considers to be the imaginary number. So it's always good. Check to see if I will work. Good. Okay. So you notice it automatically spits it out in Cartesian form. And fortunately for us, J also works. MATLAB is smart enough to understand both of these as the imaginary number. Okay. So take your pick. It doesn't matter. Okay. So let's go ahead. Let's take a moment and let's see if I can do a side-by-side screen here. Maybe. Oh, good. Let's take a moment and let's just type this in. So we recall that we use square brackets to indicate that we will be doing a matrix. And you can use spaces to indicate separate columns, semicolons to move to a new row. So I'm just going to write this, and don't forget your parentheses here. Those parentheses are going to be important. So I will just go ahead and write this, and you can follow along, or hopefully you're actually writing this down in MATLAB as well. So I'll leave it as a fraction, plus 1 divided by 60j. Okay. So there's my b, and then I have negative 1 over 10, my c. Lastly, negative 1 divided by, generous use of parentheses is always a good idea, 2.4j. Next one, negative 1 over 10. Next one, here we go, 1 divided by 3.2 plus 2.4j, and parenthesis plus 1 over 10 minus 1 divided by 20j. Close parenthesis. There we go. So again, it automatically just sticks everything into Cartesian coordinates for us. Well, let's go ahead. Let's put b in. And we have 120, 0, and 0. Okay. And if you want, you can always take a look at what the inverse of A is going to look like. Okay. So again, it's not immediately clear. You know, it's doing the same Gauss-Jordan elimination process that we've talked about previously. It's just that it's also making sure that anytime it ends up with a j in the denominator, it moves it to the numerator. And then it keeps going. So it's doing those row operations that we learned way back when. It's just doing it with imaginary numbers included. Kind of nice. Now, fortunately for us, we can also do the inverse of A times B. And boom, there's our answer. A lot simpler, right? So the first one just gives us 120. That's the potential at A. And then the other two are taking 100 and multiplying by those vectors. Hopefully everything's the same. Should probably double check that, shouldn't we? Yeah. So I'll go ahead, let me move this out of our way, and I'll go ahead and write these down for us. What we have from the MATLAB is that VA, the potential at A, the potential at B, and the potential at C are equal to, put 120, that one's no surprise. The second one is 110, and I'm just rounding, plus 6j. And the third one is 96 minus 36j. And again, now we're off and running like a bale of turtles. Can use the difference in the potentials divided by the impedances to get the currents. Certainly a lot easier using MATLAB, eh? Once you have the equation set up. Pretty cool, huh? Yeah, good. Okay, well, I think that's long enough for this example problem. We'll probably queue up another one. But again, just because I've given you this tool using MATLAB to invert the matrices, you need to make sure to understand what's going on and be able to do it by hand if necessary. Okay? So hey, I thank you for your attention. Keep up the good work. I'll see you next time.